Hello everyone, thank you very much. So, nice to meet you all. My name is Oisin Kyne. I'm CTO and co-founder of Obol, and today we're going to be talking about should you run distributed validators. Sweet. Before I get started, I just want to give a little bit of context around who Obol Labs are and what the Obol Network is. Obol Labs is a research and development team based all over the world. We have 25 people on the team at this point and 15 advisors. Obol Labs' goal is to work on decentralizing and making more fault-tolerant the Ethereum and other proof-of-stake blockchains. And the Obol Network more broadly is basically the community of people and teams that are involved in this effort. There's more than just Obol Labs, and you'll see more of that as we go along. So, what are distributed validators? Let's start at the top. So, everyone here, I'm more or less assuming, knows what an Ethereum validator is. This is the thing that drives proof of stake for Ethereum. It's basically a private key that signs a message every 6.5 minutes. These things are very important to keep online, and they're very important to keep these private keys secure. A distributed validator is a validator where this private key is split into shares, like a 3 of 4 multisig, or a 5 of 7, 7 of 10, etc. These nodes all then play a consensus game to decide what to sign. Then they all sign with their partial private key, and then Obol and the software and the middleware combines these private keys together to form a legitimate signature for that validator, which it broadcasts to the network, and it looks like a normal validator to everyone else. What this means is you have a highly available validator for the first time. That's a Web 2 word for saying you can have a machine go offline and no big deal, your validator stays up. The same way, Google doesn't go offline when they update software or a machine dies, validators in future should be more or less the same. Distributed validators makes you more resilient to software failing. If you have a mix of different software clients, let's say, for example, what happened last week with the kind of Prism and Teku issue, you'd be more resilient if your full validator isn't just running on one software. You're more resilient to hardware failure. We'll get into this a bit later in the slides, looking at disks die, machines don't live forever, so being resilient to this is important for uptime. A more extreme one is private key compromise. As I alluded to, if someone steals your hot wallet or your validator private key, they can slash you. Whereas with distributed validators, if you do a distributed key generation, no one entity has the full private key. So it becomes much more difficult for someone to steal the full private key. In the minimal example of a 3 of 4, someone needs to compromise 3 machines to be able to get a full private key. And kind of related, and the last one is, rather, if you right now, a lot of people delegate their stake to someone, you're putting extreme trust in that entity. And if they go rogue, become a bad actor, there's very little you can do. If instead you're using a distributed validator and only kind of a subset of the nodes become malicious, so 1 out of 4, no big deal, your validator will stay online and things will be okay. So how is this architected? How does this actually work? So one of the things around Ethereum proof of stake is that it uses the BLS signature scheme. And what's fancy about the BLS signature scheme is that you can combine signatures of the same hash or the same object relatively easily. You don't need access to the private key. You can just add 2 signatures together. This is important because it means you can build a read-only middleware that enables distributed validator technology. What that means is you put Charon is the name of our first client. It's built in Go, and it sits in front of a consensus layer beacon API. And each of the Charon nodes in your cluster talk to one another, and they basically just do a quick consensus game saying, hey, we have to sign something next slot. What are we picking? They decide on a hash, and that's about it. At that point, your normal validator that's sitting there controlling your private key, maybe it's keeping them in hardware, doing something fancy, they just sign a message, assuming it doesn't break the slashing rules, and they send it to what it thinks is its consensus client. That's where Charon as a middleware intercepts the signature, shares it with its other nodes, and once any of the machines gets 3 or 4 signatures, or a threshold of signatures, they can just combine them all together and hand them upstream to the consensus client. And from then on, it looks like a normal validator to the rest of the network. So the goal of this talk was to talk about, should you run distributed validators? So the first question I'll talk about is when mainnet, and where are we in that journey? So we've been working on distributed validators since as early as before DevCon5 in 2019. More formally as Obol Labs, we've been working on this since about 2021. We've been doing DevNets for the last year or so. The first major one we did was Athena. We deployed our first validator on mainnet just at the end of last year, so it's running for 4 or 5 months now. This year we did our beta testnet, which is our second larger testnet. We'll look through some of the stats on that in later slides. And as of about a month ago, we kind of finally gave the green light for our alpha launch, which is, max 1 validator, give it a try. So far we have about 7 mainnet validators, and the plan was to bring it to just 25 and chill there and see how things go. The goal is to get more production data to see how this performs in the mainnet setting as opposed to on Gurley. And yeah, that's kind of where we're at so far. And now I get to talk a little bit about performance, numbers, data, and all that type of stuff. So from these kind of first data points on alpha, you have some interesting info here. I will admit I was going through this last night, and out of some of these data, there's one distributed validator we have that I won't name names, but it did have an outage for 3 days. So you'll see it kind of represented in some of the moving averages and stuff, and that's the only validator that didn't have 2-3 nines worth of uptime. But yeah, I think the main problematic data point, as you can see highlighted in yellow, is of our first 9 proposals, 2 were orphaned and 2 were missed. So as you might guess, latency is an important part of a distributed validator. For attestations, it's not too bad, but for proposals, you have the guts of about 4 seconds to get a proposal out. So depending on how far away your nodes are, that will impact whether or not you are likely to miss a slot, or what happened in 2 cases, they were orphaned, in that proposals made, broadcasted, but it wasn't fast enough to not get kicked out. So still getting good data on that in mainnet. It's normally okay unless you get too optimistic about how far your nodes are apart from one another. We'll look a little bit about latency in further slides. So here are some graphs in line form. The first one is validator effectiveness. The green kind of drop is the smoothed variant of 3 days being offline for one validator. But without that outage, these things are more or less polling negligibly different between your rocket pools, your attestants, which are kind of 2 reference examples for mainnet validators, your kind of protocol and your centralized one. And the other figure we have on the right are your inclusion delays. The inclusion delay is a good piece of data around, how soon you're getting on chain. This particularly matters if you're slow, your rewards are downstream of your inclusion. If you're getting included late, your rewards won't be as high. The real big spike here, I actually believe, is related to the exits hard fork and trouble just after it. I have the unsmoothed graph, but it's a bit noisier. And then on the right-hand side, the spike is related to the Prism and Teku issue that were happening recently, where we lost finality. If you lose finality, you're missing a lot of blocks. Inclusion distance goes up. So that's why everyone's taking a step up. So the data set that we have more information on is our testnet on Gurley. And as I alluded to, we ran, BA was the name of our testnet. We've segmented them here into professional node operators and home stakers, and we've restricted to the 90th percentile, or the top 10% of our home nodes. Validator effectiveness on both are pretty good. As I alluded to in Gurley, about 20% of nodes are offline. So effectiveness doesn't look like mainnet. As you can see here, the network average is only 37.5% effective. So 52, 49 are both very strong numbers for Gurley. Uptime, only okay. The correctness, again, this relates to if you're missing slots, the correct answer is not always obvious depending on who proposes blocks. And the inclusion day are actually quite strong for Gurley. I believe I have them in line graphs here to give a better example. This actually is talking about cluster size. So a distributed validator, the smallest number of nodes you can have for the fault-tolerant QBFT protocol is 3 of 4. But you can also have, larger clusters. So we've been doing tests being like, does it make more sense to have 4 nodes and only, 1 node worth of tolerance? Or maybe we go up the high end and have 10 nodes and 3 of them can be offline. The trade-off, as you might guess, is cost. Running more nodes is, more work. But if you have, a group and a community of people that want to run nodes and they're like, yeah, let's all, collaborate and run a distributed validator together, higher number of nodes are more flexible. And assuming the latency is okay, meaning you're all in the same continent or so, there is more or less a negligible difference between a 4-node cluster and a 10-node cluster. The data we have here, I think, shows that if you look at the BA public, there's more or less no difference in inclusion delay and in effectiveness. The BA pros, I don't know what happened with that 6-node cluster. There might have been something wrong. And then, yeah, similarly, these graphs this time are on Gurley, so they're much noisier than they were on mainnet. And you can also see, rather than effectiveness of like 98%, your effectiveness for everyone is around the 60 mark. And then inclusion delay, rather than being 1.01 or very close to it, it's actually about 1.6 because you're missing 20, 30% of blocks, so you're only getting in later than you'd expect. This is the graph I'm most excited to show, and this is a validator. This is actually a validator I'm running, well, apart with 3 other people. It's a distributed validator, and it's showing the red marks are times where at least, well, one of the nodes were offline. They had some form of outage, and the green line, as you can see, stays high. Normally, if you've an outage, you go to 0, you're offline. Whereas here with distributed validators, so long as a supermajority are online, no big deal. So I think the worst of them, you can see a slight impact in effectiveness. I think that was actually my node that was offline. But broadly, you can actually keep a validator online even if you have some outages. Here's kind of some screenshots of our Grafana dashboard and our monitoring. And what we're showing here is that even though 1 of 4 nodes was offline, this distributed validator was still able to make a proposal. And yeah, the yellow and blue lines on the bottom left show that it was able to do the RANDAO protocol and propose properly. So even if you have some of your machines offline, you shouldn't miss your proposals. And yeah, one data point I have actually relates to the beacon chain disruption. Paul from Everlasting is one of our early mainnet adopters running nodes, and he was very happy to see that none of our mainnet nodes went offline during the finality issue. Granted, we have a lot of Lighthouse involved, and Lighthouse wasn't vulnerable, but it was nice to see that 60–70% of the network missed slots and no DV did. So that's one of the things I'm pretty happy about with distributed validators, and the goal is to prove, yes, you run a 4-node validator, keep 4 different ELs and CLs in there, and if any of them have a 0 day, you should be okay. So the last thing I'm going to talk about a little is, what does it look like to go forward from here? So as I alluded to in the roadmap, this is kind of an alpha software so far. We're testing in prod, gaining more data, getting more comfortability with it in production, integrating into more people's stacks. But the current variant, we call it a version 1. Why do we call it a version 1? Effectively, you currently can't prove at the solidity or cryptography layer who is online and who is offline. You can do it, with your monitoring. You can say, hey, that node is offline, but proving it to a smart contract is quite tricky. We've looked at it for a long time. Donkrad, back in 2019, was talking about custody games, trying to figure out, it's called the lazy validator problem. It's how do you prove that one person isn't being lazy and just kind of coasting? And effectively, the work is to make a distributed validator protocol that is provable. And if you can have proofs saying, yep, I was online, I did take part in consensus, I did submit my threshold signatures, I can prove I have access to a fresh beacon state, combining all of these together into a succinct proof that you can use in an ongoing game are the building blocks you need to have distributed validators where you don't know and don't trust your counterparty. In version 1, to some extent you need to trust them. You need to, blow them up on Twitter if they're offline, or you need to take them to court if things get really extreme. But the long-term goal is that you speak their language, you don't know who they are, you're just like, sure, let's run a distributed validator, protocol works, if you're offline you're losing money and it's being distributed to the people online. This research will be over a number of years. It has work in attributable consensus, attributable threshold signature schemes, and proof of custody games or proof of access to the beacon state. There's going to be quite a lot of work in it. You'll hear me talking about it basically every talk I give for the next few years, and I'm very excited to kind of dig into the nitty-gritty of that kind of over the coming months. That's more or less everything I have for you at the moment. I'd like to say thank you very much for the time to present to you all, and I'd like to know, have anyone any questions for me? Thank you. I see some questions.
All right, we'll bring up here first.
Yeah. So I have a question which is directly to you and your team. When running this whole architecture, is there any flaws or cons that you're afraid of at the time when this is going to go big? Are there any security flaws that you are afraid of that could happen to jeopardize the whole architecture, the whole system?
So I think your question was, are you concerned about particular security concerns about our architecture or design?
Yes, correct.
Yeah. So in short, we spent a lot of time trying to make this as trust minimized as possible, really go down the kind of keep it simple, stupid kind of design. One of the major decisions on that, as I alluded to, is making Charon be a middleware. What this means is other than helping you create the private keys, it facilitates a distributed key generation. After that, you take the private keys away from Charon. They sit in your Web3 signer, they sit in your validator client, they sit in wherever you want. So if ever there's a scenario where the software is compromised, the blast radius should be liveness, not safety. And the main risk right now, having one middleware implementation, is if it fails, you might run the risk of going offline. And the mitigation to that is to have multiple implementations of this. And yeah, that's something we're actively working on, as I alluded to, with a distributed validator protocol rather than a distributed validator implementation. My biggest fear when it comes to validators is being near the private keys, promising to encrypt them, transmit them, do anything fancy like move them from one operator to another. I don't really want to be involved anywhere near those things. Similarly, networking is another one. A lot of projects have kind of a centralized gossip network where all the messages flow across. This is problematic because normally there's at least someone running kind of message brokers that share messages around the place. If they go offline, your connectivity drops. Obol, instead, each cluster establishes direct TCP connections with one another. So the goal is that Obol can go offline entirely and no cluster gets disrupted. So yeah, safety concerns, I'm relatively okay. I will acknowledge that there's still liveness concerns, but we're working on that both at a networking layer and also on a protocol and implementation side of things.
Okay, I think we've got time for maybe one more question.
Cool. How's it going? Big fan of DVT. I think it has a lot of potential in the future. Who would you say your target demographic is? Like, is this for people who say don't have 32 ETH but want to contribute to being a validator, maybe grouping up with their friends, maybe each of them have 5 ETH or 3 ETH and they find 10 other friends who have the equal amount and they can be validators then? Or is this more targeted towards like LSD projects or larger projects that want to divide up their risk?
Great question. The short answer, I'd say this technology can be used by every validator, but different types of validators use it for different reasons. So the home staker, as you alluded to, at this point, the price of a validator is prohibitive for more or less everyone, and the goal is, not to end up in a world where only people with $60,000 lying around can stake. So we are very focused on allowing the long tail of small validators to collaborate and share a stake. We see this technology as the analog of mining pools. Back in the early days of Bitcoin, everyone just mined solo. They hoped to get a block every now and again. And within about 18 months, they were like, this is prohibitive. We need to start to share. We see distributed validators being the same thing for proof of stake. It's, everyone ran their own validator. They hope to get a proposal once every couple of years. And now it's like, okay, we need to share validators. We need to kind of break them down and work on them in groups. However, there's also a lot of reasons for them to be used on the kind of more enterprise side of things, both in the centralized provider and for the liquid staking protocols. The centralized providers, they're using distributed validators to reduce their operating costs. Most of them, because you couldn't have a validator go offline, they built something very expensive that runs in the cloud. They have kind of ways that they can take off the keys. They've never gone into bare metal because if a bare metal machine dies, you just have to sit there and wait. Whereas now with fault tolerance, you can move towards bare metal machines, commodity hardware, have simple fault tolerance, and the centralized providers can massively reduce their operating cost because a lot of them are frankly underwater because they designed them when ETH was 4K and the APR was 10%, and now neither of those things are true. And then the third person, which I think is actually the one that is most important to me, is the liquid staking protocols. These protocols right now recruit node operators and hand a really large amount of money over to a node operator and pray that things are going to go to plan. The biggest Lido validators each have about $700 million in stake, and Lido more or less has to trust them. Those node operators can disappear, they can go offline, there's very little they can do. These protocols would much rather say, you 4 operators are sharing stake. So then if one goes rogue, goes offline, no big deal, thing stays online, crisis averted. So that's the one that, liquid staking protocols, people are using them. The goal is to really decentralize them and not have a situation where one org has a huge amount of a protocol and kind of can hold them to ransom. Yeah. Okay, I think that's all the time for questions. Thank you very much, and I'll let you on to the next talk. Thank you, guys.